Let's talk about how to identify the type and location of discontinuities in a rational function. So a rational function, to remind you, is a function that's p of x over q of x, where p and q are both polynomials. So here's an example of a rational function. And basically all I'm going to do is show you how to apply ideas that you already know. So you recognize from before that this is the same as x plus 3 times a fancy form of the number 1. X minus 1 over x minus 1. So if you were to imagine the graph of this is actually the graph of x plus 3, like this, only when I multiplied by the fancy form of 1, it removed a single value from the domain of the function, because now x equals 1 is undefined. So we have put in a hole. We've put in a removable discontinuity right there. So whenever you have a rational function where you have factors that are the same in the numerator and the denominator, those factors form a fancy number 1, which is what inserts a removable discontinuity. Usually in problems, this will be somewhat disguised because you're not usually given a problem in factored form. Usually you might be given something like this. You might be told, what are the discontinuities of x squared plus 2x minus 3 over x minus 1. And what you have to do is realize, aha, you can factor the numerator, and now you can identify what factors cancel, creating the removable discontinuities. Okay, what about this one? So this one, hopefully you recognize that the denominator there is the difference of squares. 25 is a square number. X squared is a square number. So this is the same as 5 minus x times 5 plus x. And here I've got x minus 5. And it's not obvious that anything here immediately cancels. But remember, there's one more factoring trick. X minus 5 is the same thing as the opposite of 5 minus x. So see what I did? And you could, well, think about it this way. If I was to multiply this back in, the negative would apply to the 5, giving me my negative 5 here. And the negative would apply to the negative x, giving me positive x. So it's sort of like I took a negative sign out of each of these to the outside. So each of these flipped signs. And then because I like to have the positive number first, I just also reverse the order that they're in. This is a pretty common trick that you see a lot of the time in calculus to simplify things. So it's helpful to be able to just immediately pull it out. Just say, oh, like x minus 1 is the same thing as the opposite of 1 minus x. Like be able to go back and forth between those. So now that we've done that, you see that there are some things that cancel. So this is a fancy form of the number 1. So I know that I've got a removable discontinuity at x equals 5. But I also have a factor down here at giving me another discontinuity at x equals negative 5. So if I plug in x equals negative 5, that produces a 0 in the denominator, but a non-zero value in the numerator. And that was characteristic of a vertical asymptote, if you remember. So in this example, let's like rewrite this as what the graph would be. It's like I've got negative 1 over 5 plus x times the fancy form of 1 times 5 minus x over 5 minus x. So this is the thing that gives us the removable discontinuity, but the rest of the graph looks like just a transformed 1 over x family. I have 1 over x and I've shifted it. It looks like left by 5. And then I flipped it upside down. So it would be this kind of graph, but then I also have a removable discontinuity at 5. So there would be a hole right here. And this is negative 5. Oh, wait, that's way better. I should have been doing that the whole time. If you're a little bit rusty and you don't immediately recognize this as a transformed 1 over x family, think about it this way. So I've got 1 over x. If I shift it left by 5, you would probably do this, 1 over x plus 5, but that's obviously the same as 1 over 5 plus x. And then if I put a negative sign on the outside, that's like a vertical reflection. So I just sketched this here by having a picture of this graph in my head, the 1 over x graph. I just imagined it shifting left by 5, and then, oh, I didn't flip it. My bad. And then it would flip. It would flip this way, and then the hole would be here. Cool. So it would be something more like that. And I'm not actually asking you to produce full graphs here. I'm only asking you to identify the location and type of the discontinuity. But it's helpful to be able to visualize, if you can, what's going on for the whole function. But the answer that we would be looking for here is removable discontinuity at x equals 5 and vertical asymptote at x equals negative 5. Let's do a last example. So here, well, let's compare and contrast. So if I had this, x squared minus 1, this would be very similar to the last example. So in the denominator, this would factor as x minus 1, x plus 1, and then I'd have a removable discontinuity at x equals 1, and I'd have a vertical asymptote at x equals negative 1. In this example, the denominator doesn't factor over the real numbers. Because all of the roots are complex values. And you can see that very clearly if you ask yourself, when would the denominator equal 0? When would it be true that x squared plus 1 equals 0? And if you solve for it, you've got x equals plus or minus root of negative 1, which is the same thing as plus or minus I. So what that shows us is that there are no values of x that would produce zeros in the denominator, and so this function is actually defined for the entire domain of all real numbers. So there are no discontinuities for this function. And it's just good to have seen this particular example because this crops up sometimes, and actually you can use it to your advantage if you need to build your own function where for some reason you need to insert some terms that don't actually create any discontinuities to them. All you do is you figure out what are some prime factors that you can put in there that aren't factorable, and so therefore won't produce any discontinuities for you.